Okay, today we are going to discuss about addressing format. Okay, so how to give the addressing in Siemens PLC, what format they are using. Okay, the format is identifier, byte number, dot, byte number dot, bit number. Okay, so identifier means symbol. Identifier means symbol. Okay, means they have different files in your CPU like PII, PIQ, bit memory, timer, and counter. Okay, which we are discussing in the last class, right? So to give any address, okay, or to identify your inputs, I cannot write the total name PII1, PII2 like that, right? You can simply do the symbol for this. Okay, for inputs we are using I, for outputs we are using Q, for bit memory it's M, for timer T, and for counter C. Okay, so we continue now. So here for PII inputs, we are using I as a symbol. For outputs, we use Q as a symbol. For bit memory, which is a temporary memory, for that we use M as a symbol, timer T, and counter C. Okay. So here, if you remember this concept, like one bit is equal to 0 or 1. Okay. The status of one bit can be 0 or 1. That means here, if I take group of 4 bits, it's called one nibble. If I take group these bits in a group of 8 bits, that is 1 byte. Similarly, 16 bits is equal to 2 bytes equal to 1 word. 32 bits is equal to 4 bytes is equal to 2 words. That is also known as double word here. Okay. So this concept you must remember. Okay. This is a similar concept for all the PLCs. They are using bit byte for double word concept. Okay. For addressing or storing your data in this format. So this is what PLC like in Siemens is having a bit memory, right? So we see the addressing concept with the bit memory, then the symbol is M. Okay, so this bit memory is depending on your CPU. Some CPUs are having only 1024 bits, some CPUs are having 2048 bits, like that, 65536 bits, or more than that also. Okay, so your addressing format is in terms of byte. Okay, byte number dot bit number format. So we need to convert this number of bits into bytes. So how to convert? So you need to divide this. Suppose your CPU is having 2048 bits. Okay, so you need to divide this 2048 bits by 8. So it becomes 256 bytes. Okay, that means the byte numbers here are starting from 0 to 255. Total bytes numbers will be 256. Okay, then let's see how to give the addressing for bit memory. Bit memory addressing symbol is M, byte number starting from 0 to 255. Here we are having different level of addressing. It's called bit level address because here we are defining the bit number. Okay, bit number means uh, in one bit how much we can, what value we can store, 0 or 1. Okay, only two status, two images. Okay, that is a bit level address. So byte level is a group of 8 bits. Okay, word level, there is a group of 16 bits. Double word level, there is a group of 32 bits. Okay, so let's see this now. M0.0. Okay, M means identifier, M, bit memory, then byte number. So first byte number is 0. In one byte, we are having 8 bits, right? So these bit numbers are are also starting from 0 onwards. Okay, so that is 0.0. Next, here in this one bit address, this is the address. Okay, in this address, bit address, I can store 0 or 1 status. Okay, similarly we are having other bits. Okay, that is M0.1, M0.2, M0.3, like this, 0.6 and M0.7. So 0 to 7 bit numbers. Okay. So this is 1 byte. Okay, totally 1 byte. So next byte will also continue. Like 1 byte is over. So next byte number changes here. Okay, 1.0 to 1.7. Like this, we are having other bytes up to 255. Okay, 255.0 to 255.7. If you count total number of bits here, okay, 0, 0, 0.1 like this, all the bits if you count, you get 2048 bits. Okay, this maximum 255 is for total 256 bytes. Okay. Now, just a second. Okay. Next, we come for the byte level address. So MB0, okay, this total 8 bits is 1 byte, right? So MB is a symbol for displaying byte level address, then byte number 0. Similarly, for other bytes, we are having MB1, MB2, MB3, like this, okay? So we are not giving any bit address here because it is a group of 8 bits. So in terms of bytes we are defining, so take P0, okay, B1, MB0, MB1, MB2 like this. It goes up to MB255. So if you remember, like we are having 8 bits in a group. So this bit status, okay, 8 bit status will be going 0 or 1. Okay. So you know binary to decimal conversion, that is exponential format 240, 241, 242, 243 like that. Okay. You can convert the bits into some decimal number. Okay. So after that conversion, we get this value for 8 bits. So our 8 bit value will be from starting from minus 128 to plus 127 only. Means in 1 byte, 8 bits memory, I can store this much of value only. Okay, means it is not enough, right? Your value will be more than this 200, 300, 500, 400, 1000, right? So that I cannot store in this 1 byte. So what we do, we go for more memory. Means we are increasing the memory size by adding 2 bytes. Okay, so MB0 plus MB1. MB0 plus MB1 means 2 bytes means one word, right? 2 bytes means one word. So these 2 bytes I'm adding MB0 and MB1. That means this total 16 bits are coming under this one word. So addressing is MW. So I'm adding 0 and 1. So first byte number here. So 0 we have to take here. Okay. Similarly, for next one, it will be MW2, not 1. If I take 1, it will be if I take MW1, so it will consider MB1 and MB2. But MB1 is already used in this word. Okay, MW0. So what happens? The memory overlapping will happen and we'll get the wrong values. Okay. So to avoid that, we take another byte number. So the MB2 and MB3 I'm adding, so I take MW2. Next will be MW4, MW6 like that. Okay. Now, so it goes up to MW254. So in this, you can store up to minus 32768 to plus 32767. Okay. So this much of value only I can store here. Okay. So it is only up to 32,768. Now, if I'm having value more than this, like 40,000, 50,000, like that. Okay. So I need to again increase the memory size by adding these two words. That means it becomes one double word. It becomes one double word. So MD0, right? MD0 will be having these two words. Okay, MW0 and MW2 means it is having 4 bytes. It is having 4 bytes and total 32 bits. Okay, in one double word. Similarly, next double word address will be MB4, okay. Then next will be MB8, next will be MB 12, like that, okay. It will go on up to MD252. But if you are using MW0 somewhere, okay, you cannot use MD0. You should use MD2, like that. Okay, MD2 if you use, it will be like MW2 plus MW4 combination. Then you have to take MD6 because next byte number will be available. So like this, we have to share this memory, this number of bits to byte, byte to word or double word. Okay, if you are using word somewhere, you cannot use the same memory as a double word. Okay, it will overlap. Okay, if you are using any byte, so take word for another next number. Okay, otherwise it will overlap. Okay, so in one double word, you can store this much of value minus 2147483648 plus 2147483647. Okay, now just a second. Now, so this is about the addressing concept here. Similarly, for your inputs, you have to use I as a symbol in place of M, okay, and Q as a symbol for outputs in place of N, okay. So here we are having a similar concept, same concept for inputs and outputs, okay, addressing. It is about the CPU and bit memory concept. Next, we have signal modules. Signal modules means the IO modules, okay. In short, we call it as SM. If you see in the Siemens, they are having some product number starting from 6E7, SM321, 1BH01, 0AB0. Okay, so this 1BH01 is also known as MLFB number. Okay, in German abbreviation, this called as machine, not machine, manufacturer's label fabrication number something. But in English, we call it as machine readable catalog number. It's like a catalog number to select your module. Okay, so this number, these 5 letters will be different for different range of modules. Okay, so like we are having SM. SM means signal module. It can be digital or analog. Okay, we are having some code here 321. So to identify your module, whether it is digital or analog, we are using this code. Okay, so 321. The 3 stands for series, 2 means digital, 1 means input, means 300 series digital input module. Similarly, for output module, we are having 322. Okay, 2 means output here. Next, we are having different range of input modules like 8DI, 16DI, 32DI, maximum 32 digital inputs in one module. Next, for output module also 8DO, 16DO, or 32DO max. So these modules are also available in combination like mixed module, so 8DI by 8DO, 16DI by 16DO combination. Okay, and depending on your source, like input and output types, sensor type, or supply requirement, like RAM control DC, 48-volt DC, 120-volt AC or DC, different supplies. Okay, 240-volt AC. So, so each module will have different supply options. Okay, so one module is having say 1, 2, 3, 4 type. Another 16DI, 4 types. Okay, 32DI, 4 types of supply. So like that, each model will have different option. Okay, supply option. So this number will differ according to the properties here. Okay, then for your mixed module, you can see SM323. Last, the last you can see 3. Okay, 323. That is mixed DI by DO module. Okay, similarly for the analog module, SM331. 3 means series, another 3 is analog, 1 means input, 2 means output. Here we have 2AI, 4AI, or 8AI maximum module, 2AO, 4AO, or 8AO maximum outputs or inputs in one module. Okay, so 332 is for output. Similarly, we have mixed module like 334. Okay, 4 is there, not 3, here 4. Okay, so it's a mixed AI by AO model. And there are different ranges here. Okay, 4 AI by 4 AO, 2 4 AI by 2 AO, any combination you can have. Okay, now this is about the SM. So this SMs means DIDO modules, okay, and CPU are connected in one rack together. Okay, so this is called rack system. It's called rack system. One second. Cover this first. In the rack system, here your CPU and IO modules are connected together, okay, on a rack. So here you can see there is a back rail, okay. On this rail, we have to mount our CPU and power supply modules and IO modules, okay. First, we have to connect a power supply, then CPU module, then IM, then IO modules. Okay, this is for your S7300 system. So these modules are having specific slot number starting from 1 to 11. So total 11 modules we can have, including power supply module. Okay. Then slot number 1 is for power supply, 2 is for CPU, 3 is for IM. Then 4 to 11 we connect IM modules. So here you can see the numbering. Okay, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So here these are called byte numbers. Okay. So in one digital input module or digital output module, maximum 32 digital inputs or 32 digital outputs we can have. 32 digital input means 32 bits. Okay, 32 bits. 32 bits means how many? 4 bytes. Okay, how many bytes? 4 bytes. So you can see in one module we have 32 bits means 4 bytes starting from 0, 1, 2, and 3. These 4 bytes will be there. Similarly, next bytes 4, 5, 6, 7, the next slot. Like this, it goes on up to the last slot 11, 28, 29, 30, and 30 rack. Okay, so this is called one rack here. Okay, rack number 0. Then IM is used for expansion. Okay, if you need more IOs, you can expand one more rack here. Okay, for that IM is used. Okay, IM stands for interfacing module. So here from slot number 4 to 11 we can connect SM, CPs or FM. Okay, CP stands for communication processor. This is like if you need additional communication option like a different protocol, we are having Ethernet, okay, Profibus, MPI. Okay, for that expansion we can add additional card. Okay, from slot number 4 to 11. Then FM means function module. Function module means some special modules for like high speed counting, servo application. Okay, additional module. Okay, which support the servo operation, encoder communication purpose. Okay, like that, such function modules we can add here. Okay, from slot number 4 to 11. But if we are expanding the next rack, okay, we are expanding one more rack. Here also we can connect one power supply, but no CPU here. Then we have to connect one IM in slot number 3. Okay, so this IM to IM communication will be there. Means only one CPU can handle more IOs, okay, which are expanded using IM. Then slot number 4 to 11 more IO modules we can add. But the distance between these two racks, okay, is called expansion rack 1. Between these two racks will be 10 meters only. Like this, I can expand more racks, okay, 2 more racks. You can see last one is expansion rack number 3. So the maximum distance between 1, 2, 3, 4 racks can be total 30 meters only. Okay, this can be total 30 meters only. So suppose if my process is not within 30 meters, it is 50 meters or 100 meters away or 1 kilometer away, means I cannot use this configuration, right? Because it does not support that long distance communication. It supports only within 30 meters of distance. Means you need to use one more PLC for next process. Okay, like that you need more PLCs. Okay, in such case. So nowadays it is actually an older version now. Okay, nowadays we are not using this concept. We are using Profibus concept. Okay, remote IO communication purpose. We are using Profibus. Here you can see just now we discussed about this rack system, right? So in the CPU we are having two ports. One is MPI, other one is DP port. So in slot number 4, suppose if I connect any 16 DI module, okay? 16 DI means 16 bit. 16 bits means 2 bytes, okay? So this taking this 2 byte number 0 and 1. So 1 byte is having 8 bits, right? So I0.0 to I0.7. 0 to 7, 8 bits, right? Then I1.0 to I1.7. Okay, another byte. So we are just changing the byte number here. Similarly, for output 16DO means 2 bytes again. So 4.0 to Q 4.7, Q 5.0 to Q 5.7. Now, what about this byte number 2 and 3 which are not used here because we are connecting only 16DI module bit module here. Okay, 16DO module we are connecting here output. Okay, it is taking 4 and 5. But for output, we are having 0, 1, 2, 3 starting byte numbers also. Similarly for DI, right? It is 2 and 3 I cannot carry forward here, or 0, 1, 2, 3 I cannot directly carry forward here. Otherwise, I can change this byte number in software. Okay, through software also you can change this in the CPU properties. Else, if you use any remote IO module from this DP, okay, DP stands for decentralized peripheral, right? For connecting long distance uh, IO modules. Okay, from this DP we expand one module. Okay, one cable is used. That's called Profibus cable, or we are having Modbus cable. We're having CAN bus, device net. Different protocols are available in the market, but here Siemens is following Profibus communication. Okay, so this Profibus was Siemens proprietary initially, but now they have made it open bus communication. Okay, means you can also add any third party modules. Okay, not only Siemens module. So you can have extension here. With this extension, we connect one IM. IM means interfacing module with this DP. Okay. Then with IM, we add some DIDO modules. So here, like 16DI, if I connect and 16DO, I'm connecting with this IM. These byte numbers are transferred here to this remote IO module. Okay. For DO, it is taking 0 and 1 because in this rack, in this local expansion for output, byte number 01 are not used, right? It is starting from 4 onwards, byte number. But 01 has to be used. So that is available on remote IO module. Similarly, we can have one, okay, we can have the addressing here 2.0 to 2.7, 3.0 to 3.7. Similarly for the output. Okay. I can have one more expansion, okay, with this IM. So for DI, it can use 4 and 5 now. For output 2 and 3. Okay, I'm using 001 only here, right? So 2 and 3 I'm using here. So when you expand more remote IOs, okay, so whichever byte numbers are not used here, that is available on the remote IO expansion. Okay, those byte numbers will be transferred automatically to the remote IOs. So here you no need to calculate whether uh, 01 are used or not. Okay, this will be already calculated and displayed in your software itself. Okay, you can directly check them in the software. Okay, then we're having the wiring concept here. So you can see for your input module, okay, wiring diagram, wiring and block diagram of SM321. Okay, this is your overview of the module. On this module, we are having some LEDs. Okay, this LEDs for your first byte. Okay, 0 to 7 bits are there, right? In one byte, we are having 0 to 7, total 8 bits. So this is one byte. Okay, complete one byte. Another byte is there at the bottom. Okay, 2 bytes will be there. This for 16-bit module. Okay, you can see DI16. That is DC 24 volt. Okay. Now on this module we are having one connector. Okay, on that connector we are having these numbers 1 to 20 pins. On that connector we can connect the inputs and outputs. Okay, so at 1 and 20 you can see we are connecting on what 24 volt DC supply. Okay, so this diagram is available on the module also. Okay, there is a cover on the module. You can open the cover and you can see this addressing. Okay, and wiring diagram. So here from 1 and 20 we connect 24 volt DC. Okay, M means common. So it will be L here written on the module L, that means load. Okay, then we are having a switch. The switch is having two wires. So one end of the switch is connected at number 2 and other end of the switch is connected to the positive end of the supply, 24 volt DC. Means what happens here, the switch is open right now. When you operate the switch, that 24 volt DC supply is entering into the module, right? So like this, all the inputs are connected here at the positive end. So we are getting the signal through this input. Okay, when the supply is entering into the module, we get that signal. Similarly, 2 to 9. So 2 to 9 means bit numbers are starting from 0 to 7. Similarly, 12 to 19. Okay, 12 to 19. 10 and 11 are not required or not used here. Okay, because internally also they are not connected. For inputs, you don't need to use this 10 and 11 because these inputs are directly connected to the load. Okay, or 24 volt DC positives end. Okay, so when you operate the switch, supply is already entering into the module. Okay, through this terminal. Okay, or pin. Okay, so you can see the overview of this module. We're having these pins 1 to 20. So from 24 DC to MCB to SMPS, right? Which is converting your 230 volts AC to 24 DC. This supply is connected at L plus. Okay, here it is not required, and the common end is connected to the 20. Then your switches are connected from terminal number 2 to 9. Okay, and other end of the switches are connected to the load L plus. Okay, which is your 24 DC. Then all the inputs, okay, are connected on this pin numbers. Similarly, from 12 to 19. These are the respective addresses for that. This is one byte. Say byte number 0, byte number 1 I am using. This is for the 16 DI at the left side. Similarly, for right side, we are having 16 DO. You can see similar 21 to 40. Okay, so we can have 4 bytes, right, in one module, 32 bits. Okay, means 4 bytes. So 1, 2, 3, 4 like this. So I'm using a mixed module for wiring, displaying the wiring. So left side is for 16 inputs, right side is for 16 outputs. Here we have to power up your 21 and 31, which are your load. Okay, directly we are connecting with the same supply. Then outputs. Okay, this is the symbol for your outputs. Boxes symbols will be there. So one end of this box is connected to the terminal, other end is connected to the common. Okay, that means when you get the signal from the CPU, okay, to which output should be on. So what is happening here is supplies entering, okay, for syncing inputs. Okay, for your input supplies entering into the module, that's called syncing inputs. Okay, syncing supplies entering into the module, that's your syncing. Whereas here at the output supplies coming out, that's called sourcing, because we are giving supply to the output. Okay, that's called sourcing outputs. So generally in industries we are using syncing inputs and sourcing outputs. Okay, sometimes we use sourcing inputs also. Okay, but in that case we are reversing the supply here. Instead of connecting to the positive, we connect this to the common. Okay, means that sensor is taking supply from your module itself. Okay, in reverse. Okay, whereas here we are giving sourcing. Okay, supply will come out from here to the load, is called load. So because your load will be of different types, okay, source, it can be of 24 volt AC or 230 volts AC also in some cases. So we are having output modules of two types. One is electronic and one is relay type. If it is electronics, only 24 volt DC supply you can connect at the output. Okay, but if it is relay type, you can connect voltage, DC voltage or AC voltage. Okay, any one of that you can select. Okay, so this is how we connect the wiring here. So one end of this output is connected to the common. This output is like a load, so it is taking source and supply from the output module itself. That's the sourcing outputs. Okay, so you can see the similar diagram for digital output 322 SM. Okay, L plus and M. This box symbol, okay, one end of this box symbol is connected to the common of this supply. Similarly, for another byte, we are giving separate supplies for this outputs because this to this we are connecting load. Okay, load means which will be taking more supply. Okay, for that you need more uh, source. Okay, depends on the load. Okay, that's why we are connecting separately. Whereas for inputs we are getting the same source. Okay, it is enter when you are opening the switch or sensor is on. The signal is going into the module. So for that we don't need to connect this 10 and 11. Whereas here it is a output. That's why we are connecting. Okay.